In this video, we'll look at the integration or the area of the peaks. The NMR spectrum not only distinguishes the types of protons, but also how many of each type are contained within the molecule. Each peak in the NMR is therefore proportional to the number of hydrogens that generate it. An example of an NMR spectra is shown here, which includes the integrations. Integration can be shown in two ways, either a number at the bottom of the peak representing the area of that peak, or is an actual integration line, where we can measure the heights of the peaks to make it proportional to the number of protons. In the following slides, we'll examine how to use both of these to figure out the number of hydrogens for each peak in our NMR spectra. Quite often when we run an NMR on a new compound, we do not know its formula, but we can still figure out the integration of the peaks with the formula not being known. If we follow the steps where we use the ratio of the areas, and then we'll set the smallest area equal to 1 hydrogen. One thing to note about this is do not use the carboxylic acid hydrogen peak. Carboxylic acid exchanges with the solvent, so that hydrogen peak is typically less than 1. Once we've set the smallest area equal to 1 hydrogen, we divide all the other areas by that lowest number. If the ratio does not contain whole numbers, then we adjust the ratio by multiplying if needed to get a whole integer. So now let's look at an example of this. If I look at my NMR here, I can see I don't have a formula, but I have areas under the peaks. I have 51.0 and 76.8. Now note your compound will not have 51 hydrogens or 76.8 hydrogens of any given type. So now we're going to take our areas and convert them into numbers of hydrogens. Since 51 is the lowest, we're going to set that equal to 1 hydrogen, which means with our 76.8, we're going to divide it by that 51, and that will give us about 1.5 hydrogens. If this happens, then we double all the areas to give a whole number of integers for hydrogens. So if I double my 1 hydrogen, I get 2, and if I double the 1.5, you get 3. So that means in this compound, we have a ratio of 2 to 3 hydrogens for our peaks. And since the formula is not known, this would be our final answer for the integrations. Our peak at 3.5 would be 2 hydrogens, and our peak at 1.2 would be 3 hydrogens. So now let's look at what happens if we know what the formula is. If the formula is known, we'll divide the area of each peak by the total area. Then we'll multiply that number by the number of hydrogens in the formula. Once we do that, we'll take our answer and round it to the nearest whole number. So let's look at an example of how to do this. If we take our same spectra that we looked at before, but now we know what the formula is. The formula is C4H10O. I still have the areas of 51.0 and 76.8. So now what we'll do is we'll take that 51.0 and divide it by the total. 51.0 plus 76.8, the total area in my hydrogen NMR spectra. We'll do the same thing with the 76.8. Once you know what that number is, you then multiply it by 10 hydrogens. Both get multiplied by 10 hydrogens because we have 10 hydrogens in our formula. If your formula had 6 hydrogens, you would multiply it by 6. Once we complete the math operation, we get 3.99 hydrogens for our first peak, which gives us approximately 4 hydrogens. And we get 6.00 hydrogens for our second peak. So that means the ratio for my hydrogens is 4 hydrogens for the peak at 3.5 and 6 hydrogens for the peak at 1.2. So you can see it still has the same ratio of hydrogens in the peak no matter which method we use. We still end up with either a 2 to 3 or 4 to 6. So whichever method you do, both can work. So now let's look at what happens when we need to measure the heights of the integrations. Sometimes your integral values are not given or given for multiple peaks. You can still determine the area of each peak by measuring the height of the integral instead of just looking at the area number at the bottom of the spectra. It's usually best to measure your heights in millimeters so you can be as accurate as possible. So we can see in our example spectra here, our first peak integrated to 12.17. The next integration covers 2 peaks. So you can see the next integration actually integrated 2 peaks instead of just 1. It integrated both peaks as 60.65. And then our final integration was 49.78. So if we're to take a ruler to measure our integrations, we can split that integral, the integrated 2 peaks, into each separate peak. So what I mean by that is you'd measure with your ruler the bottom of the integration to the top. So you'd measure that distance. With the one that integrated 2 peaks, you'd measure the bottom here, and then you'd measure till it started flattening out. That would be the integration for the first peak. The integration for the second peak would be where that flattening out was to the top. And then finally, your third peak would be measured from the bottom here to the top here. So if we were to have taken a ruler and measured the integrations, our first integration ended up being about 30 millimeters. Then the next integration was 64 and 63 millimeters. Our final one ended up being 89 millimeters. So if we have something like this, we'll take the smallest height, set that equal to 1. So that means 30 millimeters equals 1 hydrogen. So then if I take my 64 and I divide it by that 30, that gives me approximately 2 hydrogens. Same thing with that 63 divided by the smallest one, that equals approximately 2 hydrogens again. And then finally, we'll take that 89 and divide it by the 30. That's going to equal approximately 3 hydrogens. So if your NMR spectra integrates more than one peak, you can still figure out the area of each peak by measuring the heights of the integrals. So now you guys should be able to figure out the area of the peaks for if this formula is unknown, if the formula is known, and also if your spectra happens to integrate more than one peak at a time.